Welcome back. This lecture will be on Landau Fermi Liquid Theory. This is the last examinable topic of the course. After this, we'll move on to BCS theory of superconductivity, which is very interesting, but it's not examinable. So Landau Fermi Liquid Theory is basically the study of strongly interacting fermions. We've studied interacting fermions in the last few lectures, and everything we've done has really been based on the theory of very weakly interacting fermions. For example, we started with first-order perturbation theory, and that, by definition, is accurate only to first order in the perturbation, where really you're comparing the energy of the perturbation, the interaction, to the Fermi energy, which is the other scale in the system. But also Hartree-Fock and RPA are approximations that work very well for weakly interacting fermions, but do not work well for strongly interacting fermions, typically. However, the physical systems that we're usually interested in as condensed matter physicists usually have very strong interactions between the fermions. So the interaction energy, E interaction, is typically larger, or at least approximately equal to, the other scale in the system, which is the Fermi energy. And this is whether we're thinking about electrons in metals, whether we're thinking about helium-3 fermions, whether we're thinking about neutrons in neutron stars, whether we're thinking about electrons in semiconductors. It is almost always the case that the interaction energy is much stronger than the Fermi energy. You might think for a second that in semiconductors we might find an exception, because you can tune the density of electrons in a semiconductor. And in fact, in particular, you can make the density of electrons much, much lower in a semiconductor than it is in a metal. However, this, unfortunately, goes in the wrong direction. It makes the interaction energy larger compared to the Fermi energy, because, well, the interaction energy is, for Coulomb interaction, is on the scale of E squared over epsilon naught A, where A is the typical spacing between the fermions, whereas the Fermi energy is h bar squared over 2m A squared, where A is the spacing between fermions approximately. There are constants which I've left out. And so if you go to very low density or large distance between the fermions, both of these quantities, both the interaction energy and the Fermi energy, get smaller. But in fact, the Fermi energy gets smaller faster, so the ratio of interaction energy to Fermi energy actually gets bigger. So semiconductors are more strongly interacting than high density. Low density semiconductors, where the density of electrons is very small, are actually more strongly interacting than high density of electrons in metals. So the problem is even worse in semiconductors. So nonetheless, the calculations we've done so far, they're not useless. We can use them for a lot of qualitative inspiration as to what we should expect in strongly interacting Fermi systems, but we can't really use them for anything that's quantitative. With some minor exceptions, we calculated the very high frequency response at long wavelength, and we calculated that exactly using the F-sum rule, and that's true independent of interactions. And an extension of that is that RPA at very long wavelength and high frequency is accurate enough to get the plasmon energy mode correct exactly, independent of the interaction. But these are exceptions, not the rules. Typically, these calculations that we've done, first-order perturbation theory, Hartree-Fock, and RPA, are quantitatively inaccurate unless you have a system which happens to be weakly interacting. Now, despite the fact that we have strongly interacting systems, everything that we think about physics of metals or semiconductors, the entire semiconductor industry is really based on treating electrons as being essentially completely non-interacting. We throw away the interactions altogether, and we'd like to know why this makes any sense whatsoever. So progress on answering this question was really started due to research on helium-3. And helium-3 is simpler than electrons in metals because there's no long-range Coulomb interaction, which complicates matters quite a bit. Helium-3 is a strongly interacting Fermi system, but the interaction is short range because the helium-3 is a neutral fermion. So the helium-3, as I mentioned once before, they knew it existed before World War II, but due to the American nuclear project, very small amounts of helium-3 became available for research in the early 1950s, and at Oak Ridge, which was one of the laboratories really started by the nuclear project, Fairbank got his hands on about 1 milligram of helium-3 and was able to do some experiments cooling down the helium-3 to low temperatures. So I'm going to write this down. Helium-3, the Fermi energy was sort of somewhere in the ballpark of 5 Kelvin or something like that, and he managed to cool it down to temperatures on the order of 1 Kelvin, so temperatures less than the Fermi energy, and he saw evidence of the Fermi-Dirac statistics, which was pretty exciting. Incidentally, I should mention that helium-3 now is nowhere near as rare as it used to be. It sort of has a morally ambiguous source that the helium-3 is a byproduct of thermonuclear bombs. That thermonuclear bombs are based on tritium, which decays with a half-life of 12 years, and one of the decay products, the main decay product, is helium-3, and that helium-3 has to be removed from the bombs, and the tritium has to be replaced to keep the bombs active. So the stockpile of H-bombs that both the United States and the Soviet Union, or no longer the Soviet Union and now Russia, have sitting around is producing helium-3, which becomes available to scientists, and scientists like getting this stuff not only to do research on, but also because it's an important part of many experiments. The best low temperature refrigerators are based on helium-3, helium-4 mixtures. The price of helium-3 fluctuates with supply and demand, and it can go from $100 a liter to maybe $10,000 a liter, depending on the supply and demand at the time, which is, you might say, that's expensive. It's like extremely expensive Scotch, $10,000 a liter. I mean, you can pay that much for a bottle of Scotch. Not even incredibly old Scotch, from 50-year-old Scotch can cost you that much, if you like really good Scotch. But if you like helium-3, sometimes you can get it cheap, sometimes you can't, depending on how much supply there is in the world at the time, what it's being bought up for. That's not insanely expensive. It's cheap enough that you can use it for physics experiments. I mean, the world would probably be a better place if we didn't have this ready supply of helium-3, but as long as we have the supply of helium-3, we might as well use it for experiments. Anyway, so Fairbanks in the early 1950s did the first experiments on helium-3, and he saw evidence of a Fermi-Dirac distribution. In particular, he saw a heat capacity which was linear in temperature, which is typical of typical of a Fermi system, a system with a Fermi C. The standard calculation that we do in our first year stat mech courses or our solid state physics courses, and also a Pauli spin susceptibility, magnetic spin susceptibility, which was a constant at low temperature. And both of these are a reflection of Fermi-Dirac statistics. Both of these are pretty easy calculations to do, but the problem was that the prefactors, when you look at the actual numerical prefactors of the T and the numerical value of this constant, did not fit the non-interacting fermion model. And we sort of have an idea of why it is that they shouldn't fit. We understand that there's this thing as mass renormalization that can occur due to interactions. We saw that even at Hartree-Fock level. But even if you say, well, okay, the mass is renormalized due to the interactions, still it actually doesn't fit the experiment. And the reason it doesn't fit the experiment is because the mass renormalization that you would require to fit the heat capacity doesn't match the mass renormalization that you would require to fit the Pauli spin susceptibility. So something's going on, and it left people a little bit confused, and we had to rely on the great Lev Landau to sort things out. So Landau comes into this problem a few years after these first experiments in 1956, and wrote a paper called The Theory of Fermi Liquids, a beautiful paper. Maybe I'll link to that on my webpage of Fermi Liquids. It's 6 pages long, at least in the translation it's 6 pages long. It includes exactly one citation to the experiment by Fairbanks, and it really lays out everything, well, not everything, but an enormous part of what we understand about interacting fermions in this one beautiful paper. It was a lot of it was based on his physical intuition and phenomenological thinking, but the structure that he lays out was justified later both by detailed perturbation theory and by renormalization group arguments even later. So Landau's conjecture, this is going to sound vague to begin with, but we'll try to make it more definite. So the conjecture, the Landau conjecture, has 2 parts. Conjecture, probably spelled that wrong, is that interacting fermions should be like non-interacting, but they should be dressed by interactions. I'll explain in a moment exactly what we mean by dressed. In particular, the ground state is a dressed Fermi C, a dressed version of the non-interacting Fermi C, and the low energy excitations, there we go, and the low energy excitations, low E excitations, which we call quasi particles, are dressed versions of the non-interacting case of non-int case. Okay, so this all sounds great, and it doesn't mean anything until I tell you what the word dressed means. So the word dressed here means, or its approximate means, that there should be a cloud of interactions with the surroundings. And I'll make this more precise as we go along. And the way Landau argues this qualitative picture is with what is known as the Landau adiabaticity argument. Adiabaticity, having to do with adiabatic argument. It's a subtle argument which easily subtle arguments are things that one should use with caution, but this one turns out to be right. The idea is we start with a non-interacting case, non-int case, and we adiabatically turn on, the interactions. And this adiabatic turning on of the interactions, okay, so what does the non-interacting case look like? So we have our Fermi C. Here's our Fermi C. Okay, that's oblong. Let me see if I can make it round. Okay, there's our Fermi C, and let's copy it here. Copy and paste over here. Okay, so we are going to, so this is our non-int Fermi C. And we are going to slowly turn on the interaction, and so turn on, on the interaction, and that action of turning on the interaction has to be a unitary operation. So I'll call it U. Why does it have to be a unitary operation? U equals unitary. Because this turning on of the interaction is something that can be done in a Hamiltonian in principle. The Hamiltonian could be a function of time, and as you change time, you can increase the interaction strength, and because it is a Hamiltonian evolution, it can be described as a unitary operator. Okay, so then what you get at the end of the day, after adiabatically turning on the interaction, is some sort of dressed Fermi C. So now this is the Fermi C with the interactions turned on. So this is now the dressed Fermi C. Okay, and we can play the same game. Let's see if I can with quasi-part with excitations. So let's consider an excitation of the Fermi C, a particle added. So it will be C dagger with K and with some momentum K and some spin sigma on the Fermi C for the non-interacting case. So let's see if I can paste. There's my Fermi C again. Okay, so here's my Fermi C, and I'm going to add to the Fermi C, I'm going to add one quasi-particle up here at K and sigma. Sorry, this is an actual electron operator because it's non-interacting Fermi C. Filled Fermi C, maybe make this filled Fermi C also filled. So we have a filled Fermi C, and I'm going to add one additional fermion above the Fermi C over here. And then I'm going to do the same thing. I'm going to adiabatically turn on the interaction, and what I'm going to get out is a dressed quasi-particle. So here we now have a dressed Fermi C. So it's the Fermi C plus the interactions. And in addition, there will be a particle with momentum K and spin sigma, and it is going to be dressed with its interactions with the environment as well. And so this is the dressed quasi-particle. Dressed QP, dressed quasi-particle, and this is the bare fermion. You might call it a quasi-particle as well, but it's really just a particle. There's nothing quasi about it. It's just a fermion added to the Fermi C. But over here, it's a more complicated particle because it's not only the particle with momentum K and sigma, but it also involves the interactions with its environment. Now, the important point to note here is that the quantum numbers of this excitation remain completely changed. So quantum numbers are unchanged by this adiabatic change, are unchanged. So in particular, we have a momentum K and a spin sigma, for example. And these are not changed by the turning on of the interactions, but the dressing is a cloud equals a cloud of interactions equals cloud of interactions with the environment of int with environment. And this is actually very similar to what we know from fluid dynamics. So in fluid dynamics, if you move a particle through a fluid with some velocity v, that particle will interact with the fluid, and there will be backflow around the fluid, around this particle. So the fluid will do something like this, getting out of the way of this particle. Like this is something we learned in fluid dynamics courses, and the mass of this particle so this is a backflow in a fluid, not blackflow, backflow, flow in a fluid. This is the interaction with the environment, and this has the effect, for example, of changing the apparent mass of the particle as it moves through the fluid. Now, why does this picture of dressing particles as you turn on the interaction, why does this make sense? Why is it that we should think of the quantum numbers as being completely unchanged? as these quasi-particles as being discrete objects, just like their non-interacting brethren. Well, the correct way to ask this question is not why does it make sense, but how could this fail? How can this fail? And we can, okay, how can this fail? One way it can fail is there can be a first-order phase transition as you turn on the interaction, and you can go to a completely different ground state. So, for example, you might start with the Fermi C, and you turn up the interaction. At some point, it could just make a transition to a crystal, a so-called Wigner crystal of particles, in some lattice or something like that. And that's just that's a complete failure of the approach, because the new ground state is not adiabatically connected to the old ground state. It's completely different, has completely different symmetries, completely different properties. That's one way it could fail. So one possibility is first order phase transition. But assuming there's no first order transition, so assume no first order transition. How can this picture fail? Transition. How can it fail? The only way it can fail is it fails if and only if, if and only if the quasi-particle decays into multiple excitations. So here's our picture again. As we turn on the interaction, we have one excitation here with some momentum k and a spin sigma. We turn on the interaction adiabatically, and if this dressed quasi-particle has a decay process by which it scatters into multiple quasi-particles, which each have their own momentum and their own spin, then this picture fails. It means that the identity of this single excitation is lost in the process of turning on the interaction. Okay, and Landau's point is that this doesn't happen, that the quasi-particle does not decay into multiple other quasi-particles and lose its identity. So it retains its identity, it retains its momentum, it retains its spin. So why is that? Let's try to figure out why it is that it cannot decay. So this doesn't happen. This does not happen. Okay. So again, we start with our Fermi C. That circle is becoming very useful with a single. Let's call it K1 just for convenience, and sigma 1. So it starts. This is without the interaction, and we're going to turn on. Again, we're going to turn on the interaction here, and the process we're interested in is a process by which this K1 and sigma 1 scatters into several other quasi-particles, and maybe some quasi-holes too. So this one will be maybe K2 sigma 2, and this will be maybe K3 sigma 3, and this will be K4 sigma 4. So if this process occurs where this particle at K1 sigma 1 then decays into multiple particles here, then we've lost the identity of the original quasi-particle. The quasi-particle picture no longer makes sense. So let's think about this process in a different language here. So what we have is coming in, this is sort of Feynman diagram-ish, or scattering theory sort of diagram. So K1 sigma 1, it's going to scatter to K2 sigma 2, and via an interaction create a particle hole pair where this one's K3 sigma 3 and this one's K4 sigma 4, and there's going to be some amplitude for doing this, which is going to be VK2 K4 K3 K1. So in this sort of Feynman diagram, you annihilate K3 and K1. These are the incoming arrows, and you create K2 and K4, which are the outgoing arrows. The key point here, is that due to the phase space restrictions, assure that the scattering lifetime scattering time for this process, tau, goes as K1 minus Kf to the minus 2 power. And we'll show that in a moment. This is the time, tau. Can be calculated in Fermi's golden rule if we want. But if this is true, that the scattering time, it goes as K minus Kf to the minus 2 power, it means when K1, in this excitation here, is very close to the Fermi energy, so K1 minus Kf is very small, then the scattering time gets extremely long. And when the scattering time gets extremely long, you get closer and closer to the Fermi surface, the scattering time gets very, very, very long. It means that the quasi-particles near the Fermi surface are long-lived, and eventually, if you get close enough to the Fermi surface, they live forever. So tau going to infinity implies these are eigenstates. They never decay. Okay, so this is the whole point. This is the whole shooting match, as they say, that as you get close enough to the Fermi surface, these excitations just never decay, meaning that they're eigenstates, and they retain, even with the interactions turned on, they retain their character as being quasi-particles, and they retain their momentum and they retain their spin. So what's the proof that this process doesn't occur due to phase space restrictions? It's pretty easy to do this. That if you do a Fermi golden rule type calculation, you're going to have you have to conserve, well, we always have to conserve momentum and energy. So here we're going to be concerned with conservation of energy. That's going to imply that when we do a Fermi's golden rule calculation, the scattering time, the inverse scattering time, it's going to involve an integral over all the three possible final energies. So energy 2, energy 3, and energy 4. And these energies can't be any bigger than the initial energy that this particle had above the Fermi surface. Remember that the energy of a hole beneath the Fermi surface is a positive number, as the energy of a particle above the Fermi surface is also a positive energy. And as you get closer and closer to the Fermi surface, that energy gets very small. And so both the three final products, E2, 3, and 4, the three final products, all have to have energies which are less than E1, and their total energies have to add up to E1 also, E2 plus E3 plus E4. So that's the energy conserving delta function. And if we just sort of think about this integral here, what it's calculating is it is calculating in sort of in three-dimensional integral here. This axis is E2, this axis is E3, this axis is E4, and we're calculating the area of, I'm going to draw this different color, blue. We're calculating the area of this triangle here, which intersects each axis at E1. That's what this integral represents. Okay, that the sum of the three, it's supposed to be an equilateral triangle despite my bad drawing, the sum of the three energies should be E1 in the three directions, and so it's the area of this equilateral triangle that we're looking at. Now, the area of that equilateral triangle area obviously goes as E1 squared because it's an area, and well, E1 is K1 minus Kf. So so this tells us that, as claimed, that the time scale. So this is giving us the scattering rate here. So the time scale blows up as K1 minus Kf to the minus 2 power. Now it is possible to find certain highly interacting systems where the scaling of the scattering time is not K1 minus Kf squared. These are sometimes called non-Fermi liquids or marginal Fermi liquids, but they're extremely unusual. But I mean, they're of a lot of interest for things like high temperature superconductors, where it doesn't behave like a Fermi liquid for one reason or another. Okay, so let's ask a little bit more. What does this dressing look like? What does this dressing of the Fermi surface look like? What does this cloud look like? So again, maybe just this picture. Let's just copy this picture again. Maybe copy the whole thing. Well, this picture. It's this picture we want here. Let's copy it again. We're copy and paste it down here. Paste. Okay. So what does this dressing look like that we're interested in? Well, we know that this dressed Fermi C, well, if we call the Fermi C, we'll call it ground state 0, GS0, meaning non-interacting here. And the dressed Fermi C is going to be our unitary operator on ground state 0. Okay. We can also do the same thing with the particle excitation operators. So the quasi-particle excitation operator, the thing that makes a quasi-particle, is going to be the dressed version of the particle, the operator that makes the particle in the non-interacting Fermi C. So this is a come on. So this is the QP creation, and this is the bare fermi, non-int fermion creation operator. Okay, so everything we're interested in is what is buried in these unitary operators here. So that's where things get interesting. Well, we can, to get some intuition for what's going on, let's start calculating the properties of the dressed Fermi C order by order in perturbation theory. So this thing we'll call psi ground state. Maybe we'll just call it ground state, GS. Like this. And we're interested in what's the property of this ground state. So let's just calculate it in first order perturbation theory or second order perturbation theory. So the ground state, the interacting ground state, is going to be, there's going to be some normalization constant, which I guess I'll call eta, and then there'll be the 0th order in interaction is going to be the non-interacting ground state, and then we'll have a sum over excited states. I guess we'll call that n. And then we'll have, this is just the usual perturbation expansion, ground state 0 over En minus E naught plus ... And we can even write out exactly what this matrix element looks like in more detail. This is eta ground state 0 plus so what is this? This is the kind of thing we were doing before. What can this interaction applied once to the ground state give us? Well, the interaction is C dagger CC. So this is going to have to be some Q1, Q2 greater than Kf, Q3, Q4 less than Kf, C dagger Q1, C dagger Q2, CQ3, CQ4, I'm dropping the spin indices in case you didn't notice, and that's all applied to ground state 0. And the amplitude for that is VQ1, Q2, Q4, Q3, and the energy of that excitation is going to be, compared to the ground state, is going to be EQ1. I could probably usually write it as epsilon naught Q1 plus epsilon naught Q2 minus epsilon naught Q3 minus epsilon naught Q4, and then there'll be dot dot dot. And we can write out this series, to as many orders as we like. Now let's consider what is the occupancy of electrons in a particular state K. So what is the expectation of the number operator in a state K in this new ground state? So this is going to be ground state. The number operator is going to be C dagger K, CK, ground state, like this. And that will be, well, okay, it will be ground state 0, unitary operator, C dagger K, CK, unitary operator, unitary dagger up here, unitary operator, ground state 0. And the key here is, okay, so whether you want to look at it this way or maybe it's easier actually from this formula, this is what the ground state looks like. That we know in, like this, let me plot number of K as a function of K, and here's Kf. We know that in the non-interacting Fermi C, this is a step function. So this is non-interacting. And in the interacting Fermi C, what's it going to look like? Well, from the leading term, which still looks like the bare ground state, there is still going to be a step at Kf. From the other terms, there's going to be corrections to this occupancy. So some of the states below the Fermi surface are not going to be filled. Some of the states above the Fermi surface are going to be filled. So let me actually draw it maybe in red. Got it, red. And it will look something like this. But it will still have a step at the Fermi surface, and then like this. Okay? And typically the magnitude of this step is known as z, where 0 is less than z is less than 1. For a non-interacting Fermi C, the size of the step is 1. It goes from fully occupied to fully unoccupied at the Fermi surface. But for an interacting Fermi C, there's a step, but the step only takes part of that value. Okay, so there is still a step in number occupancy of the original fermions of the actual fermions at Kf at the Fermi surface. Maybe I should say at the Fermi surface. But if I tried to calculate the number operator of, the number, expectation is what we calculate of that operator. The number operator for the quasi-particles, that is expectation of C twiddle K, like this, twiddle, sorry, not C twiddle, C twiddle C, C twiddle K, C twiddle of K. This thing is actually a step function of step 1, of magnitude 1. Why is that? Well, because we're looking at ground state, C twiddle K, C twiddle K, ground state. The ground state is a unitary operator on U0. The C twiddles are unitary times the bare C. So this is C twiddle. One. C twiddle dagger. And then we have unitary C K, unitary dagger. And then we have unitary on ground state 0 here. So the unitaries all cancel, and this is just ground state 0, C dagger K, CK, ground state 0. So this is the same as non-interacting, as non-int. So if we are interested in the quasi-particle occupancies, the occupancy of these dressed objects, the occupancy of these dressed objects is this blue step function. They're completely, quasi-particles are completely filled below the Fermi surface and completely empty above the Fermi surface, although the electrons are not completely filled below the Fermi surface and are not completely empty above the Fermi surface. So this brings us to a rather important theorem. Theorem by Quinn Luttinger, Joaquin Luttinger. I believe he was working at Columbia in the 1950s and 60s, known as Luttinger's theorem, which has two parts. One, you can define a Fermi surface by the discontinuity in n hat k, where this n hat k is the occupancy of the electrons. The discontinuity may not be of magnitude 1. This is for the bare fermions here, not for the quasi-particles. The discontinuity may not be of magnitude 1, but the discontinuity will be there nonetheless. And number 2, the volume of the Fermi surface of Fermi C in K space is unchanged by the interactions. In particular, if we have a rotationally symmetric system, when you have a real band structure, the Fermi C doesn't have to be round. It can have any, it can have strange shapes. But in a rotationally invariant system, where we threw out the lattice, then we have a spherical Fermi C, and so in particular for rotational invariant systems, this implies that the Fermi momentum, Fermi wave vector, is fixed. Okay. All right. So, given this, Luttinger's theorem was after Landau, and Landau had sort of guessed this. Incidentally, if you know the Ward identities from field theory, the proof of Luttinger's theorem relies on the Ward identities. So given this quasi-particle concept, how is it that Landau decided we're going to describe our interacting Fermi system? Well, what he wanted to do is he wanted to describe Fermi system, Fermi liquid, by the occupancy of quasi-particles, by n quasi-particle of k and sigma. So this is the thing that at zero temperature, at t equals 0, this thing is a step function. So n quasi-particle of k is 1 for k less than kf, and is 0 for k greater than kf. Okay, I'm now going to make two changes of notation. First of all, I'm going to drop the superscript qp here, so nqp notation here. nqp, I'm just going to call it n, because every n I'm going to write from now on is going to be describing quasi-particle occupancies. And the other thing I'm going to do is I'm going to work with momentum p, not k. They differ, of course, by a factor of h bar. And the reason for this is because that's typical in literature when you talk about Fermi liquid theory to work with p, not k. Or if you prefer, just set h bar equal to 1, and that will make your life easy, and there's no distinction between p and k. Okay. Actually, Landau is a little bit more clever still. He says that in fact, if we're going to do this at finite temperature, we can describe a Fermi liquid at finite temperature by using the real Fermi function here rather than a step function. But for our purposes, it's going to be sufficient to use a step function. Think about zero temperature properties. Okay. All right. So the second step in Landau's thinking is we're going to assume the perturbations are small. Perturbations to the Fermi C are small, so that any excited quasi-particle or quasi-hole is close to the Fermi surface, and we can write, and furthermore is not of very high magnitude, and we don't make many of them. And we're going to write the change in the quasi-particle occupancy is going to be n p sigma minus n naught, which is just the step function of p sigma. So this is the ground state occupancy, and this is the physical occupancy, and what we're going to measure is delta n. We're going to assume that delta n is small. So we're going to Taylor expand in this parameter delta n. So we'll write a free energy, or we'll actually reference to the ground state free energy, F minus F naught. And that should be, writing out an expansion, well, it'll be a sum over P and sigma. We'll write EP minus mu times the occupancy of P and sigma, and there'll be ... like this. So a comment here, that this EP minus mu, the energy of the quasi-particle momentum mu, we can always write that as some effective Fermi velocity times P minus PF, and this is going to be the energy of this excitation. P minus, we can always write it as distance from the Fermi surface times the Fermi velocity. We're not implying EP is not equal to P squared over 2m. It doesn't have to be, the mass can be anything we want. It could be unrelated to the bare mass of the electron. It could be normalized very highly by the interaction. So I'm just going to write it as some V star times P minus PF. Okay. Now, well, okay. If we want, we can write VF is some PF over M star here. Okay. This M star is a phenomenologic parameter. M star. Okay. We're always allowed to linearize around the Fermi surface, so we're always allowed to write this form. Now, this looks like it's a nice first term of our expansion, but it's a little more subtle than that, and that's something that, of course, it took Landau to realize these things, that this first term is already second order in small, because we have P minus PF is small, and delta N is also small. So we have quadratic in small already, and so we have to look for other terms that are also might be quadratic and small. And there is indeed another term which is quadratic and small, which is the interaction between two quasi-particles, or two quasi-particle densities. So let me write out now the additional correction term that we didn't, that Landau uses, and I didn't write here in this equation here. So the first term is exactly what I wrote here, so let me just copy it. Well, okay, copy this whole thing. Copy. This is very convenient that I can do these copying. I can't do this on chalkboard, can you? Okay, so this is the first term. Make it a little bit smaller. Oops. There we go. There. Okay. And then we'll fill in the first ... term. This is the interesting one. It's going to be 1/2. I'll write it this way: sum p prime sigma prime, some function f sigma prime, some phenomenological function p comma p prime, delta n p sigma delta n p prime sigma, and then plus dot dot dot. Now the dot dot dots now are small cubed, so we can throw them away. And this f function here is some arbitrary interaction between a quasi-particle going in direction p with spin sigma and another quasi-particle going in direction p prime with spin sigma prime. Now this term here is representing the interactions between two different quasi-particles. And the important part of this form here that we've written is that the interaction term allows the energy to shift. It shifts the energy due to the presence of quasi-particles going in two different directions. So quasi-particle going in one direction, quasi-particle going in the other direction, those two interact with each other. But it does not allow the quasi-particles to scatter from direction p to some other direction, p double prime. The direction in which the quasi-particles are going remains fixed. And this is based on Landau's understanding that the quasi-particles, if you're close to the Fermi surface, the quasi-particle state is an eigenstate, that it doesn't scatter into multiple other quasi-particles with different momenta and quasi-holes. It stays going in the same direction, although its energy may shift due to the presence of other quasi-particles that might be around. Okay, maybe a quick comment here that we've used. So comment. We've written things in terms of sigma and sigma prime, which are spin up and spin down. More generally, you might have to worry about the case where spins are pointing in, say, the x direction or something, in which case you have to reformulate everything in terms of a density matrix, delta n sub alpha beta of p, and the spin of that quasi-particle is going to be some trace of the Pauli matrix, beta alpha, delta n alpha beta, and this f is going to have a bunch of indices representing representing the contraction of these density matrices. We're not going to need that, so I'll maybe I shouldn't erase it, but I'll wall this off so we don't use it. But just so you know that the Landau approach can be generalized to handle particles that are polarized in any direction. Doesn't have to be. We don't have to think in a particular basis of spin up and spin down. Okay. Let me make this a little smaller here. So then the next step is we want to calculate the energy of a quasi-particle that happens to be going in a direction p with spin sigma, and the way we do this, and this energy can be adjusted by the presence of other quasi-particles due to this interaction term. So we write this as the derivative of dn p sigma of here we go, of the free energy functional. So this e twiddle p sigma becomes, well, we'll write it reference to mu. E twiddle minus mu is going to be EP minus mu. I guess probably, this thing is to be minus mu also. No, I think I wrote it correctly. No, it should be minus mu, like that. Is EP minus mu. That's this factor here. Maybe I'll even write that out again. That's this factor. This is VF star P P minus PF. And then there's the interesting part, is the part due to differentiating this interaction term, and it gives us the following: sum over P prime sigma prime F sigma sigma prime P comma P prime delta n of P prime sigma prime. So that the energy of a quasi-particle going in direction P sigma is affected by the presence of quasi-particles going in other directions P prime sigma prime. Okay. Now, at this point, we do a bunch of math to manipulate things around and make it simpler to work with. This is really the fundamental equation here that describes the physics of the quasi-particles in Landau Fermi Liquid Theory, but it then becomes useful to try to simplify things a lot, and I think a lot of times the physics gets lost in the simplification, but if you want to make actual calculational progress, you have to go through the simplifications. So let's go use some of these simplifications. One, we'll assume P and P prime are near the Fermi surface. I guess we already assumed that, near Fermi surface. So that means that f of pp prime, I'm not drawing the sigma indices, we can write that at f of p hat p prime hat, and then by rotational invariance, so rot invariance, if I'm using a rotationally invariant Fermi surface, I can write that at f of theta p prime. So I only care about the angle between p and p prime. So this interaction between, well, these are all vectors, between a quasi-particle going in direction p and a quasi-particle going in direction p prime only depends on the angle between p and p prime around the Fermi surface. These now are hats, p hat and p prime hat. Well, when we have a function which is defined as an angle on a sphere, we then usually decompose it into harmonics. So decompose into harmonics. So we can write f of theta is going to be sum over harmonics with angular momentum L of FL PL of cosine theta, where these PLs are the Legendre functions, which presumably when you learned about spherical harmonics, you learned about these. And then we can invert that transformation if we want, that FL is integral from -1 to 1 d cosine theta PL cosine theta f of theta, and I think the normalization gives these a 2L plus 1 over 2. So that defines this this expansion. An example of this that we'll use is the 0th harmonic is just 1 over 4 pi integral over the entire sphere of f of theta pointing in that direction. Okay, and the first harmonic will be the integral of f times some cosine factor. Okay, good. So that's simplifying the way we write f. The second simplification is that we're going to use spin rotational invariance, spin rot invariance. So that means that FL up has to equal FL down and FL up equals FL down up. These are the two spin indices. So remember that F had two spin indices on it, F of sigma and sigma prime. So by spin rotational invariance, up must equal down and up has to equal down up. And so it then becomes useful to define the so-called symmetric combination, 1/2 F up plus F up down, and the antisymmetric combination is 1/2 F up minus F up down. Okay, so those will be useful simplifications and just notational simplifications. And then 3, F has dimensions of energy, dim equals energy, and we can see that again by going back to our constituent equation here. So this is an energy, delta n is an occupancy which is dimensionless, and so this is F has dimensions of energy, and it's useful to construct something dimensionless. So let's let d star of EF, this is an effective density of states, this is volume at times m star pf over h bar cubed pi squared. This is a density of states, of states. I think we calculated the density of states at the Fermi surface for non-interacting fermions. It looked exactly like this, except instead of m star, we just had m here. Now we're putting an m star here, so this is now a renormalized density of states at the Fermi surface for some m star. And m star, remember, is related to the Fermi velocity, which is a phenomenological parameter of the problem. And then we will define, okay, the density of states has dimension equals 1 over energy. So if we define F, capital F, symmetric, antisymmetric of L, as d star EF, small f, symmetric or antisymmetric of L, this thing is dimensionless. Okay, so with these parameters, these are known as the Fermi liquid parameters. Fermi liquid parameters, and along with kf and m star, they completely parameterize my interacting Fermi liquid. So Fermi liquid is described by kf, m star, then the series f0 symmetric, f0 antisymmetric, f1 symmetric, f1 antisymmetric, and so forth, this whole series. Now, they're not all independent, and as we'll see in a little while, that m star is actually related to f1 symmetric, for example. So in principle, we have to go up to as many at high harmonic as you like, but for most experiments that you would ever do, only the first few of these Fermi liquid parameters matter at all. So you end up parameterizing your Fermi liquid with a very few number of parameters. And what's the meaning of these Fermi liquid parameters? Well, they're basically, so the F, L are energies, energy renormalization factors for deforming the Fermi C, the spherical Fermi C, in harmonic L. So, for example, F0 is associated with taking a Fermi C, which is round, and deforming it in a zeroth harmonic, in other words, stretching it or compressing it. F1 is associated with the first harmonic, so you take your spherical Fermi C and you stretch it in one direction, like that. That's a first angular momentum mode, and so forth. Okay. Now, the index symmetric or antisymmetric, S versus A, is whether the spins, both spin states, do the same thing, or whether they do opposite. So, for example, if we start with a Fermi C like this, and if both spin states go out at the same time, so up and down, that's F0 symmetric, whereas if I start with my Fermi C here, and the down spins go in, whereas the up spins go out, then this is F0 antisymmetric. So the down spins here are compressed, and the up spins are expanded. So we can go ahead and we can actually start calculating, at least in perturbation theory, for weakly interacting fermions, we can calculate F. So let's actually start by calculating small f. Small f is an energy. So this is interaction energy, int energy, between quasi-particles at p and p prime. Again, this comes from the quasi-particle assumption that that you are allowed to change the energy of the quasi-particle, but you're not allowed to scatter it from one momentum to another. So the kind of diagrams you have are the following. This, basically using the language that we had before, we have we could have something like a particle with P coming in, and it can have P coming out, and has some Q interacting with some P prime and P prime here. So if this is a quasi-particle with momentum P coming in, it has the same momentum P going out. This one has P prime coming in, and this has P prime coming out, and they interact with momentum Q. This Q obviously has to be 0 to conserve momentum at each vertex. So this value of this diagram is V at Q equals 0, and this is what we called before the direct interaction. If we used a neutralized background, we would set this term to 0, but we don't necessarily have a neutralized background for short-range interactions like helium-3. But there's a exchange or Fock term in our interaction that we can do something like this. So we can have P here, and then P prime coming out here, and then P coming out here, and P prime coming in here, and then the momentum exchanged is P minus P prime along that wiggly line in the middle, and this is then going to have this diagram is going to have value minus V because it's an exchange term, minus because it's exchange, or Fock term, and the momentum exchanged across this line here is P minus P prime. And in order to have such a term here, the spins have to be aligned. Otherwise, you can't exchange the Fock terms only occur if you have the spins aligned. So we can have F up down of P prime. This will be V of Q equals 0. This is the direct term. And whereas F up of P and P prime will have both the direct term and the Fock or exchange term, P prime. And this V of P and P prime, we can write it as, this magnitude of P and P prime is basically 2pf cosine theta, because P and P prime are close to the Fermi surface, and then we can Fourier transform this appropriately to get the F sub L's. Okay, so should we keep going? Maybe we should stop there and just do. We don't have that much to do, but we've gone on for more than an hour here, so maybe we should stop there. I'll have another small lecture to finish up the rest.